Hello everyone and welcome to this new session of our iXlive webinars. I'm Pierre Darcourt, working as a navigation algorithm engineer at iXblue, and that will be your host today to talk about the INS subject. So I'm here with Yves Paturel, our senior expert for navigation systems, and he's going to give you some insights to select the right INS. So hello Yves.
Hello Pierre, hello everyone. Welcome to those who are attending this webinar about INS, and welcome back to those who already attended the IMU webinar.
The IMU one, yeah. So a quick overview of what we're going to do today. This morning, it will be a 25 minute presentation where Yves is going to answer the questions I have. And then we will answer your questions. You're more than welcome to ask them on the right-hand side of the screen. You can write those questions and we will answer them at the end. So let's go back to the subject we have today. It's the INS subject. It stands for Inertial Navigation System. You can see that there are some examples right behind Yves of those INS. So last Tuesday, you talked a lot about the IMU's sensors. What is the difference between an INS and an IMU?
Well, a simple way to say it is that an INS is an IMU with a computer and some algorithms in the computer. And so the IMU is providing the measurements of the physical effect like angular rates and linear accelerations. And from these measurements, the computer, through the algorithms, will process the data in order to provide the 3D angular position, which is very often called the heading, roll, and pitch, and the 3D velocity, and a 3D position. And so this is the first algorithm that we have to perform in the computer. And most of the time, an INS contains also algorithms which is comparing these data which are computed only from the inertial sensors with any other external sensors. The very most popular external sensor is a single antenna GNSS receiver, but there can be any kind of other sensors like a position sensor, velocity sensors, and depending on the application, whether it's under the sea, on surface of the sea, on land vehicles, on airborne, this aiding sensor can be of different types and different accuracy.
Okay, interesting. So what you're telling is that there are two algorithms inside the INS. One is using the IMU sensors, and the other one stands for data fusion with other external sensors such as GNSS.
That's right.
Okay, so what's the first topic you would like to talk about?
Well, the first topic is related mainly to the first algorithm,
okay.
Which is we have a diagram here. So from the gyro measurements and acceleration measurements, we have some integrations which will provide from the gyro the attitudes parameters, heading, roll, and pitch. And from the acceleration, after projection on a stabilized frame, we will integrate once for getting the velocity and the second time to compute the 3D position. But as any mathematical integration, we need to know where we start from. And so we need the initial value for attitude, all three parameters. We need the initial value for the velocity and the initial value for position. But I want to focus on the initial value of heading, which is could be a little bit tricky. So okay. There are mainly three methods when you are switching on the INS to get this initial value for heading. Imagine that the vehicle is still, so not moving,
static,
and so this we could compute the initial heading with the gyros and accelerometer measurements in some condition, providing that these sensors are accurate enough. And we will come back on
so
this.
Heading only with the inertial sensors?
Yes, it's possible.
Okay.
And I will provide a few words about how to do it.
Okay.
And the second method could be to use a dual antenna GNSS receiver For this, you need to have two antennas which have some distance between these two antennas, and the GNSS receiver then will be able to provide the direction with respect to true north of the line between these two antennas.
Okay.
In order to be accurate enough, the distance between these two antennas must be sufficient. Usually we consider that 2 to 4 meters is the right distance between these antennas.
Yeah, it must be sufficient compared to the precision of the GNSS.
Yes, the GNSS is working in a differential mode between the two antennas,
okay,
but with some accuracy. And so this, in order to minimize the impact of this accuracy on the heading provided by the GNSS,
okay,
we need some baseline between these two antennas. And the third method is a method which would use another sensor, magnetometer, which will be able to measure the magnetic field. As long as this magnetic field is only the Earth's magnetic field, by measuring the three components of this magnetic field, we will be able to compute the magnetic heading. Magnetic heading is not true heading, so we will have to compensate for the magnetic deviation, but we can have some databases or tables where we can compute what is the deviation at the location of the INS.
So you need to know your position to do so.
Yes, that's right. And another problem that we may have with the magnetometer is the fact that if you are not measuring only the Earth's magnetic field, you have to compensate for all the magnetic fields which are disturbing this Earth's magnetic field. So it may come from the INS itself, from the vehicle on which it's mounted, or from the environment around the vehicle. So this method is nice because it can provide with very few sensors, which are now not so expensive.
Yeah, it's what we find in the smartphone, for example.
Yes, you have this in smartphones as well, but the accuracy is less, and it's very difficult to reach an accuracy which is better than 0.5 degrees.
Okay.
And anyway, it will depend on the magnetic environment disturbances.
Okay, well, so one of those three methods you told us is only using inertial sensors. This seems really nice, but what is the drawback of such a method?
Well, the drawback is that you cannot perform this method with any inertial sensors, because you need some accurate inertial sensors. Why? Because the principle is to measure the direction of the Earth's rotation rate. This Earth's rotation rate is a very small rotation. One turn every 24 hours, 15 degrees per hour. For example, the small hand on a clock is running one turn in 12 hours. So it's twice lower than this rotation rate, and you cannot even see it. So you can imagine that it's a small rotation rate. In order to measure the direction of this Earth rotation rate, we consider that at least you need an accuracy in the measurement of 1/100 of this Earth rotation rate. So it means that you need some gyros which have an accuracy better than 1/100 of 15 degrees per hour, so a little bit more than 0.1 degree per hour.
Okay, when I look at the datasheet of a sensor, I need to look at bias instability, bias repeatability.
Well, usually when you switch on the unit, the bias is the bias repeatability parameter.
Okay.
So since you don't have any other means to calibrate this bias, then the accuracy must be on the bias repeatability. So the bias repeatability must be close to 0.1 degree per hour accuracy, which is a rather high performance gyroscope sensor.
Oh, interesting. Well, this means maybe a rather expensive sensor. What are the other advantages of such a method?
Yes, obviously, when the most accurate, the most expensive it is. But the advantage of this is that first, you don't rely on any condition outside of the INS. So this initialization of heading can happen anywhere at any time because the Earth is always rotating. So this is the main advantage. I should be a little bit cautious, but because it would not work at the poles, South or North Pole. But if you are at the North Pole, everywhere is south, and if you are at South Pole, everywhere is north.
Yeah. Interesting, yeah.
Not same, north.
Yeah. Okay.
And but most of the time it's possible because usually you don't switch on your system at the pole itself. So this is the main advantage. And the other method, you may have some constraints. For if you have a dual antenna GNSS receiver, you need to receive the signal. So it wouldn't work inside a building. It would not work in a deep forest. It may not be working well in an urban canyon where you have a lot of multipass.
Yeah.
So there are a lot of constraints. And for the magnetic system also, if you are on close to a metallic bridge or in a metallic hangar, then this environment will be disturbed. The Earth's magnetic field will be disturbed, and the measurement will not be accurate.
Okay, so what you're telling is that if I have a bad inertial sensors, if I don't have dual antenna GNSS and I don't have magnetometers, I won't be able to find the north?
No, if you have a single antenna GNSS receiver, what you can do is start running the system. With this, you don't know the initial value of heading, but while you will be running, you will be able to estimate through the Kalman filter the heading error. And so you will converge towards the true heading.
Okay.
However, for this, you need to perform some specific features of the trajectory. For example, you need to perform some rotations and face different orientation directions with respect to north. Or you may also need to accelerate or brake. What is important is to have a variation of the velocity vector, either in direction or in amplitude.
Okay, well, interesting. So we talked about different methods. Ones are for a static vehicle, others are for a vehicle that's moving. What would you recommend?
Well, no general recommendation. It always depends on what constraints you are able to accept. If you want to have heading in static mode, either because you need it or because you don't want to start the running without this information, you need at least one of the first three methods. And even with these methods, we have seen that there are some constraints about the environment. And so if you want to have no constraint at all, obviously, you need to have a higher performance inertial system, which is able to initialize this heading by itself without any other needs. But since it's more accurate, it's more expensive.
Yeah, definitely.
So it's always a compromise.
Yeah, I understand. Well, thanks a lot for those heading information, those initialization heading information. Is there other feature you would like to talk about?
Yes. One thing we said that when you start running, even with a low performance sensors, you can provide all the parameters of the INS. 3D orientation, 3D velocity, and position. But what happens when the GNSS measurements are no more available? So this is something where the accuracy of the inertial sensor takes the most importance. Because obviously, when there is no more GNSS measurements available, you need to rely only on the accuracy of the gyros and the accelerometers for computing all these parameters. And so the main difference comes when the GNSS is not available anymore. And so it's it's rather easy to understand what happens with position. You know that the position error will grow more or less, at least at the beginning of the loss of the GNSS, as a function of the square of the time. So it's growing fast, it's exponential, but this is quite well known. One thing that is a little bit less well known is the fact that the heading will also
be impacted.
Impacted by this loss of the GNSS, because we have to rely on the accuracy of the gyro.
Well, this is interesting because GNSS is correcting the position, but it will also have impact on other Kalman states.
Yes, this is the magic of the Kalman filter. By just using a comparison on the position and by knowing the model of all the inertial sensors, we are able to compensate for some errors, like the heading error, even if we don't have a direct measurement of
the heading. Okay.
But when GNSS is no more available, then this heading will drift.
Yeah.
And so we may have some examples here how it will drift.
Okay.
So what I did for providing some examples, I took measurements from 3 different gyros, and I tried to do what is doing the Kalman filter in real life when GNSS is available. So to try to estimate the bias of the sensor while the GNSS is available. And then I imagined that no more GPS, and then I integrated the measurements from the gyro.
So we can assume that the beginning bias of this curve is really good. You've estimated?
Yes, or it has been estimated in the best way as it was possible.
Okay.
And so we see here that the heading would drift over, I took an example with 10 minutes here. We have about 1.7 degrees in 10 minutes.
Oh.
So which would, over 1 hour, we can consider it's 9 to 10 degrees per hour.
Okay.
And so this is an example. And you see that the fact that it's drifting is due to the fact that the bias is not constant, because it's varying due to a lot of parameters inside the sensor, the inertial sensor. We have another example here with this yellow curve, another gyro. This one is drifting about 0.5 degrees over 10 minutes, which would be around 2.5 degrees over 1 hour.
Not yet enough to find the Earth rotation.
No, but by the way, this is not what we are trying to do. Here is we try just to maintain the heading. We imagine that the heading was correctly computed at the start of the GNSS loss.
Okay.
And so that are 2 examples of rather medium performance sensors, and with a with a very high performance sensor. We have here an example of what we could get over 10 minutes. It's less than 1/1000th of a degree drift, and it would be almost perfect, almost no drift over these 10 minutes. Obviously, we could imagine that if it was over several hours, it would start
drifting. Yeah. Okay. So we have here the comparison of those 3 sensors.
Yes, we have here on the same scale the comparison between the drift of this sensor, and you can see that it might be very different. And this is where the quality of the sensor is having some huge impact on the performance of the INS.
Talking about the quality of the sensors on the data sheets, I can find several parameters, for example, bias instability that we talked about last
Yes.
Tuesday. How can I deduce from those parameters that this is going to happen?
Okay, let's have a look. If you attended the IMU webinar,
Yeah.
I showed these curves that are called the Allen variance curve, and we draw it. We have drawn them for all three gyros that I showed. So we have the red one here with the bias instability figure of 1.5 degree per hour.
Mhm.
The yellow one with 0.9 degree per hour, so very similar, slightly different, but very similar. And the blue one with a bias instability of less than 4,000 of degrees per hour. And if we, you remember that very often, this figure, the three figures that you can find on data sheets. So you could imagine that from these figures only, that the red gyro and the yellow gyro would
be similar.
very similar drift,
Okay.
which is not fully the case. You can see here that the red one is very different. It's at least 4 times worse than the yellow one. And we can have some explanation, even if we have very close figures for the bias instability. You see here, the bias instability is the minimum value of this Allen variance curve.
Okay.
But what happens is that for this red gyro, the standard deviation of the averaging on over time
rises again.
It rises quite short time after when you reach the minimum value.
Mm-hmm.
And so this is what we see here, the effect of this on this curve, because it shows that on period of times which are higher than 200 seconds.
Yeah, higher than the minimum, like
yes,
600 seconds.
The stability of the bias is not so good.
Yeah.
This is what we see on the red curve here. And for the yellow one, the minimum value is very similar, but it's much more stable. This is what we see here.
Okay.
And this one is very, very low. And so this is why here we have a quasi-perfect heading drift
situation. Yeah, we should wait for a longer term to see the drift of
yes.
this sensor. Okay. I think an important notion to tell here is that this is lab results.
Yes. And by the way, all these measurements were made with lab measurements of the gyro. Okay. In actual life, in actual mission, it would not be as good as it is here for 2 reasons. The first one is that the Kalman filter, before the loss of the GNSS, would not estimate as well the biases, because the Kalman filter estimates a lot of parameters at the same time.
Yeah.
And the second reason is that there are other factors which would affect the performance of the sensor and the stability of the bias of the sensor, which would be the temperature variation, the magnetic field direction, and so on.
Okay. Well, so we talk right now of what would happen with a GNSS outage, but can I observe such a drift with the GNSS?
Yeah, we would be very happy that it never happens when GNSS is available.
Yeah.
Unfortunately, even if I think that Kalman filter is a magic tool,
yeah,
it's not a universal tool, I would say.
Fortunately for us, maybe.
Yeah, there are some conditions where the Kalman filter cannot estimate some errors. We call this the observability of these parameters. And one of these parameters is the heading error, which cannot be estimated when the trajectory is a straight line at constant speed.
Really? Well, this is strange, because if I have a GNSS antenna, I mean, I will have those several points, and it makes the heading.
That's right. This is the usual way to think about it. But on especially on aircraft and on vessels,
Okay.
what happens is that the heading is not always the same as the course. As a reminder, the course is the direction of the velocity vector.
Yeah.
So we on this drawing here, we have the aircraft, which is following this straight line at constant speed, and the heading here is along in the same direction as the course. So here, and then the GNSS will provide the different points of the trajectory and even the east and north velocity, which are correct. With no specific error.
Okay.
But imagine that the aircraft, there is some wind, and so the aircraft is facing a heading which is different from the course. So the trajectory of the aircraft remains the same. It follows the straight line.
Yeah.
The velocity remains the same. And the measurements of the GNSS will be exactly the same as in the previous drawing.
3D velocity will remain the same.
Yes, and the trajectory as well.
Yeah.
But the aircraft is not facing the same heading. And so it means that from the GNSS measurements, you cannot deduce what would be the heading. Imagine that there is so much wing, or imagine that the INS is on a crab.
Yeah.
And so the crab could walk like this, and the difference between course and heading would be 90 degrees.
Wow.
So what happens in that case is that GNSS is providing exactly the same parameters, but the heading is different. And there is no way to compute the error of heading because the velocity is constant.
Yeah.
So the accelerometers are measuring zero acceleration, and zero is zero in any reference frame.
Yeah.
So when you integrate zero, you will get zero.
Wow.
So zero velocity change. So no information coming from the sensors.
From the accelerometers. Okay.
So it means that in that case, with a straight line at constant speed, what will happen is that the heading will drift the same way it's drifting when we don't have the GNSS information.
Okay, wow. So you just took the
good thing about this is that still the velocity and position will remain accurate, at least, because it comes from the accuracy of the GNSS. But heading will drift.
Okay, so you just took the example of an airplane with a ship; it would happen the same.
Yes, as long as you have not the same, you cannot make the assumption that the course and heading are the same.
Yeah.
Then you may have the problem.
This current issue in the ocean.
That's right.
Okay. Well, we talked about the ocean, the air, but what happened on land?
Well, on land, it may depend. On a car, most of the time, heading and course are very similar because the car is not skidding. Unless you are a fast driver and a very professional driver,
making fun
it may happen.
On the parking as well.
On the parking, yes, it's safer.
Yeah.
And also, if you go off-road or on a very muddy roads, or it may happen that this assumption of heading and course being the same is no more valid.
Okay.
So each time this happens, you may have the drift of the heading. But when this assumption is true, then you don't have. The best example is the train, which is running on rails.
Yeah.
And so there is no transverse velocity.
Yeah, definitely. A train is a 1D problem. And if it's not anymore on the track, then it's not our problem anymore, the position.
Well, we have to try to maintain it on the track anyway.
Yeah, definitely. Okay, so thank you very much, Yves. I hope it was not too long. You talk a lot. But,
I'm sorry.
So now it's time for some questions. You are. I hope you have asked some during the presentation, and you're welcome to have those questions right now during this question and answer session. So first question we have for you, Eve. I'm gonna read it. Can you explain again how the heading is computed using an IMU?
Yes. Okay. The heading.
I guess this
You
is
mean
this is with only inertial sensors, I guess.
Well, with inertial sensors only, yes, because it's the IMU is not computing the heading; it's the INS which will compute it. The way to do it is to we are using the fact that the definition of the direction with respect to north is the direction of the projection of the Earth's rotation rate on the horizontal plane. So in an INS, what we do, first we compute roll and pitch using the accelerometers in order to know where is the horizontal plane.
Okay, and this is not that difficult because the gravity is
the
really big.
accelerometers are measuring also the gravity, and so again, gravity is a huge effect compared to the Earth's rotation rate.
Yeah.
And so the measurement of the horizontal plane is not difficult.
Okay.
So knowing the horizontal plane, then we measure the three components of the measurement of the gyros. But when the gyro is not moving on the vehicle, the measurement of the gyros are the three components of the Earth's rotation rate.
Yeah.
Only because the rotation rate of the gyro with respect to Earth is 0. And so we project these three components on the horizontal plane, and we compute the direction of this projection on the horizontal plane with respect to true north.
Okay, well, and
this is the way we do it in INS. But as I said previously, you need to have measurement of the rotation rates with a very good accuracy, at least better than 0.1 degree per hour.
And how long must this static period last?
Well, this depends on different parameters, like the noise of the gyros and so on. So usually it takes a few minutes, let's say between 3 to 10 minutes, depending on the kind of sensors you are using.
Okay. Well, it seems that we have quite a lot of questions in the pipe. I hope you're sitting well here because we're not finished yet.
Okay, I'm
so
ready.
For autonomous subsea or surface vehicle, no USBL or GNSS data, which INS will provide the best result with the less drifting possible?
Well, the very easy answer would be the X-Blue INS, but
which one? Which one?
Well,
there are three.
Any of them. No, to be serious, when you don't have a position aiding like on subsea, if you don't have GNSS or USBL, you may have some aiding with the velocity. So you can use a DVL or an EM log, which is less accurate, but it helps anyway. And so you may have some other aiding sensor. But anyway, this velocity aiding, if you want to take the full advantage of this, you need a very stable heading information. So you need an INS with a heading which is not drifting over time, because otherwise you will project this velocity aiding in wrong direction, and then you will increase errors on velocity on position.
Okay. Oh. So I think here we have another question that you've already answered. You mentioned heading initialization. What about roll and pitch? So
well, I mentioned it at the beginning, but it's true during the whole over the mission. The roll and pitch are computed using the measurement of the gravity field, and usually we use the more or less horizontal accelerometers. in order to compute the ratio between the projection of the gravity on their sensitive axis to measure roll and pitch.
Okay. And you do it first. You start by roll and
We
pitch,
do
and
we
then
do that first, and then we use
heading.
the gyros for computing, and we have specific algorithms which will update these the drift of the roll and pitch using accelerometer and velocity measurements.
Okay.
But it will be too long to go
This,
into details.
This is lots of equations. So next one, how fast is XBlue INS settled down during initialization?
Well, usually we say that after 5 minutes we can start running.
The end of the static mode.
Yes.
Okay. Next one, can you explain how the INS works within your GAPS USBL system? Tricky one, maybe.
Well, it's a dual division question. The INS in GAPS, you know, the GAPS is a USBL. This USBL is providing angles of elevation and direction with respect to the vehicle. And so what we need to know heading, roll, and pitch, and position of the system
The INS,
in order of the INS to provide the position from the USBL. So we need mainly heading, roll, and pitch to know in which directions the measurements from the raw measurements from the USBL are measured.
Okay. Well, thanks. Another one. Could you also elaborate on the dead reckoning process applied by XBlue INS?
Well, what I must say that we do not use a dead reckoning process.
Okay.
Dead reckoning process, at least the way I
understand.
define
the
dead reckoning. Dead reckoning is the combination of two measurements, a heading measurement and a velocity measurement. Okay. And knowing the velocity in the vehicle axis and knowing roll, pitch, and heading of the vehicle, you can project this velocity into a stabilized frame, the geographic frame, and then integrate in order to get the position. So the position is computed from the heading and from the velocity.
Yep.
In our INSs, we do not compute. We compute heading, we compute velocity, but we do not compute the projection of the velocity on the in the geographic axis. All this combined in a single, first in the what I call the inertial computation algorithms, and also in the Kalman filter, where we take advantages of the behavior of each sensor. So if we have a velocity sensor, we do not use this velocity sensor, the external velocity sensor, to integrate it, but just to compare with the inertial value of the velocity. And the comparison will help us to compute some errors that we will compensate for.
This is the correction step of the Kalman filter.
That's right. So we cannot say that it's dead reckoning. Dead reckoning is not taking care of the behavior of each sensor like this. Takes measurements and make the computation directly.
It's different algorithm.
Yes.
Okay. So next one, how long would it take a military vehicle from a cold startup to align its position within a GNSS denied environment, especially without GNSS in a jammed area?
Well,
can it be faster than 5 minutes, maybe?
I'm not sure I understand correctly the question, but if the question is an INS able to self-align on position, self-initialize the position? The position. From what I understand in the question,
indeed.
There is no possibility to initialize the position with inertial sensors.
You can find the latitude.
Yes, but it's not very accurate.
Okay.
And you need very high performance sensor for that.
Okay.
But most of the time, it's not possible to do it. So you have to know the position from another means. The most popular and the easiest one is the GNSS.
Yeah.
But if GNSS is jammed, you have to know the initial position by knowing where you are on a map. And so you can input this data in the INS as a starting point.
The user will do it by itself, giving
Yes.
the value. Okay.
Yes. Or we can also we have some connections with digital maps. You can just show the points on the map, and then it could automatically initialize the value. However, it comes from the knowledge of your position on the map.
Yeah, you need to have this one. Okay, so next one, heading on a straight line, which sensor should be good to avoid that issue? The gyros?
Well, it depends how much drift you want to you can accept.
Yeah.
If you want no drift, you need a very high performance sensor for on the vertical axis.
Yeah.
Because most of the time the heading is computed from the vertical axis, unless your mission is always on the side. But most of the time, when you are more or less flat during the navigation, this heading is coming mostly from the vertical axis.
Yeah, this is the case of most vehicles.
And so you need at least this gyro to have higher performance than the other ones.
So in a kind of hybrid system would be interesting.
Yes, we are manufacturing such a system. It's called the Atlas A3, which is a hybrid system between MEMS and FOGs.
Okay, wow, nice. So next question for you. In a straight, in a straight line trajectory, what would happen if the vehicle changed velocity without altering its course?
It's
going to help.
Yes, it would help, but it has to change quite a lot, because it's the way it works is that it's the change in the velocity which would help a lot. And if you just go from let's say 100 kilometers to 98 or 95, it will not help a lot, because it's not enough. But if you change velocity vary from I don't know 50 kilometers per hour to 100. Yes, it would help a lot to keep estimation running of the heading, and then you would not get this drift as high as it would be without changing the velocity.
This is the magic of the Kalman. You have input on the acceleration, and it helps you to give the heading.
Yes,
so this is funny. So next one, I don't know this word. Does Kalman filter differ in different zones? Kalman filter, you know?
Kalman filter, maybe? Differ in different zones.
I
no,
think.
The Kalman filter itself, I'm not sure I understand well the question, but the Kalman filter itself does not depend on zones.
Maybe on the pole. On the pole, it's a different.
No, even on the pole, it knows that it's close to the pole, so the computations, providing that you took care of every details in the math, it would work anywhere.
And there is this cyclat issue as well.
Well, this is for the accuracy of the initial heading.
Okay.
Due to the fact that we measure the direction of the projection of the Earth's rotation rate on horizontal plane.
Yeah.
The closest you are to the pole, the smallest this projection is.
Yeah.
And so the effect of a bias on a smaller and smaller vector would create a higher and higher error on heading.
Yeah. Okay. Well, but this is not Kalman filter. This is initialization. So next one, should we be waiting 1 or 2 minutes after shutting down before putting the INS away?
No, I don't.
Maybe it depends on which technology you have.
I don't see why. There used to be, but this was in very old times. So you were not born, unfortunately.
Yeah. Where were you?
Yes, I was. Unfortunately, with some technologies you had, which were you had a wheel which was rotating at a very high speed. You may have waited before moving the
The
vehicle
system.
because it could hurt the gyro. But with modern technology, this is not
It's
anymore
not an
the
issue.
case. No.
Okay. Another question. There is still a lot. So, is it possible to compute heading north-seeking dynamic using? Oh, I don't have the question anymore. Yeah, sorry. I'm gonna ask it again. So, is it possible to compute heading north-seeking dynamic using a single-axis rate gyroscope with a bias stability of 0.15 degree per hour? This is
Okay. I would say that
almost enough. Yeah.
yeah. In general, no,
Okay.
because in order to measure the direction of the projection, you would need to have the three components of the Earth's rotation rate. But if you accept to put your gyro on a kind of rotating table, which allows to face different directions and to be able to know what is the horizontal plane,
Yeah.
then it could be possible with a single gyro. But you need some mechanical device around, and it would take longer time.
And this bias performance would be enough if it was
Well,
a three axis.
Yes, the performance is 0.15. You would get about 0.5 degree accuracy on heading with that.
Okay.
Because it's about 1/100th of a radian accuracy with a 0.15 degrees per hour.
Okay. Next one. So, does an INS performance change based on the depth it is used in a submarine?
Yes, for submarine applications or a subsea application,
Subsea
at least.
application, yeah.
No, the performance doesn't change with depth, providing that the algorithms are the right one.
Yeah.
Without it would be a little bit long to go in very details here, but for example, I told you that an accelerometer is measuring the gravity at the same time. So we have to subtract the gravity from the accelerometer measurements.
Yeah.
But in order to subtract it, you have to know it. And the gravity is changing with the depth. So if you don't implement the right change,
to take into account
law
this,
of change,
this mass of water above you.
Yes, the right law of change of the gravity with respect to the depth, then you would have some errors. But if you are aware of this and you provide the right algorithms and computations, no problem.
Okay. Oh, interesting. So in the event an X-Blue INS crashed during a critical operation, will it provide a predicted estimated course until it reactivates?
Unfortunately, not, and it's not only for X-Blue INS. It's for any INS. The INS will not keep memory of the trajectory unless you logged it. But if you continue moving while the INS is off, then you don't know where the move. So there is no possibility to know any of the initial values without making any assumption. If you make the assumption that it didn't move, then you can
keep the
restart on the last values which were logged before it crashed.
Okay.
But otherwise, no, it's not possible.
And this is something we do.
We do have some in our INS. Yes, we store. We log the data at the end of the mission, so that if the user wants to use this data as a starting point, he can do it, providing that when he switches on the unit, it provides the information. I want to start on this.
It's the user who decides
That's right.
to do so. Okay. Next one. So in a subsea environment with USBL, DVL, pressure sensor, altimeter, and an iXblue octans gyro, well, very precise, would it be possible to use only self-INS software offline and not online?
Let me think about, read the question in detail. Well, the Delphi-NS software is doing the same computation as the real-time computation.
It's a post-processing
So
software.
it's a post-processing software.
Yeah.
So yes, you can do this computation afterwards, providing that all the data which are processed are logged somewhere.
Okay.
And so it would be possible. However, if you do it in post-processing, you don't have any information in real time. So you don't know how to control your vehicle. What usually is done with our systems is that our systems are used in real time. We log the data, and with the post-processing software, we improve the quality of the data. And one way to very efficient to improve this is to use the past data. At each time you use the data from the past, but also from the future, because in the post-processing, you know at each time, you know the past, but also the future. And when you know the future, you are much smarter. So we are smarter when we are doing post-processing.
This is the famous forward-backward
That's right.
algorithm. Okay.
Yes.
So next one, it's about subsea once again. So are iXblue subsea INS greatly affected by pressure, salinity, temperature, and metal structures?
Well, the INS itself is not. They are not affected by any of these parameters. No effect of pressure, salinity, temperature. Aiding sensors might be affected by a DVL, for example, which is using the sound velocity in the water, needs to make some compensation due to salinity, pressure, and so on, and temperature.
Okay.
And so this aiding sensor may need to know these parameters in order to provide a better accuracy aiding measurement. But the INS itself is not sensitive.
Yeah, the IMU itself, because the INS is doing this this fusion with the Kalman filter, and if the external sensors are wrong, then
yes, but it's in order to process the inputs from the external sensors.
Okay, yeah.
And it's not due to the inertial sensors. It's due to the fact that aiding sensors might be affected by some of these parameters.
Okay, makes sense. So a quick one. Can you compare RLG versus fog?
We do manufacture fogs in iXblue. We do not manufacture RLG. We know that there are some differences and some common points. Common points is the fact that they are both optical sensors with the advantages and some of these optical sensors. But the difference in principle of the two technologies are very on very small parameters. Just in a nutshell, if I should keep only one difference between RLG and fog, is that RLG is a very good technology. It provides accurate measurements, but it has some limit to the performance, the ultimate performance you can reach. Fog, so far, we didn't find this ultimate performance.
Yeah, the bigger the fog is, the best it's going to be.
Providing that you know exactly how it works in details inside.
Okay, yes. Well, cool. So there's a quite added bigger, but not so big. Okay. Sorry. So how does a shoulder period affect the position for an underwater vehicle?
Well, the Schuller period is an effect on the the parameters that are output from an INS when there is no aiding. As soon as you have some velocity aiding, position aiding, obviously, as velocity aiding is sufficient,
Okay.
then you can damp down the Schuller oscillations.
Okay. Interesting. So next one, is one calibration done once enough, or do we have to do that for every single mission?
I'm not sure which calibration,
yeah.
which calibration we are speaking about, because in our INS we don't perform any calibration before mission.
Okay.
So I'm not sure if we are speaking for subsea applications. Maybe what the question is about what we call the DVL calibration. During this calibration, when we use on subsea vehicle DVL and INS, we need to know what is the angles between the sensitive axis of the DVL and the sensitive axis of the INS. So this is done through a calibration.
Okay.
But once it's installed on the vehicle, we have to perform it once, and it will keep running for as long as you don't dismount and remount the units. But it will remain valid for many.
You're going to do this calibration in a static mode, or
no, it's
thanks
done,
to the
it's done at sea.
to the movement?
It's done
Okay.
at sea.
Okay. Well, so one more is one calibration. Oh no, sorry, sorry.
That was the
that was the question your audience. So
Yes.
it seems like this is the last one. For subsea applications, what is the depth rating for X-Blue INS?
We do provide some INSs which are depth rated down to 6,000 meters.
Oh,
For the one which can go the deepest.
in
Some of them are going only to 4,000 meters.
Yeah, it depends on the one you choose.
Yes.
Okay. So it seems like we have no more question right now. You sure you don't want to ask a last one? Okay. So yeah, we'll be happy to answer. Yeah. Well, that's up. So thank you very much, Yves, for all those answers you provided.
Welcome.
We hope you enjoyed this this last session. And we will be posting a replay of the session on our website, and you can watch also on the YouTube channel. If you want to talk about the INS explanation from Yves to some colleagues, you're more than welcome to do so. So we have another webinar session on the 25th of June. It's going to be about ECO series, how to optimize sub-bottom profiling data. So you're welcome to assist to this other webinar, and we will perform this session also today at 5 p.m. French hour. So thank you very much for assisting the webinar today, and have a very good day.
Yes, thank you, Pierre. Goodbye to everybody, and tell your friends that if they missed it, they can still have it
on the replay
this afternoon.
Yeah.
Bye.
Goodbye.